We will now establish some properties that will help us in our work in computing determinants. There are some matrices where even if the dimension is very, very large, that if they are of a certain type, computing the determinant is very, very easy. In fact, that group of matrices to which I'm referring are the triangular matrices. Right? So let's take a look at the triangular matrices and see if we can establish a pattern for computing their determinants. Right? Now let's take a look and let's kind of do this in sequence so you see the pattern. Right? So let's say we have 2 by 2 and let's focus first on the upper triangular. Right? So we'll start with the upper triangular. So if it's a 2 by 2 upper triangular matrix, then it would look like this. You'll have A11, A12. You'd have to have a 0 here right below the main diagonal, but then you can have any numbers on or above the main diagonal. Well, let's since it's 2 by 2, that's not difficult to compute the determinant. We end up with the determinant of this matrix being A11 times A22 minus, and then we do the product of the off-diagonal elements, but because there's a 0 there, that product is 0, and we're simply left with A11 times A22. Not too bad. Let's look at the 3 by 3. Right? So if our matrix, and now let's write down the generic 3 by 3 upper triangular matrix. So A11, A12, A13, I have to have a 0 there, and I can have any number there, any number there. I have to have a 0 there, and a 0 there, and then we'll have our A33. Now, for this one, to compute the determinant, this is where we can use that theorem from Laplace that says in our cofactor expansion we can choose any row or column. Well, I'm going to choose column 1 as my expansion, right? So again, let me write it down in its full glory what it looks like. It's going to be A11 times C11 plus, going down that first column, it'll be A21, C21, and then A31, C31, right? But the nice thing is, because the matrix is upper triangular, these two entries are 0. So that's 0, that's 0. So these terms completely go away. All right, so that's helpful. So then let's write down the C11 cofactor. We're going to have A11, and then it's times the special -1 to the power 2, and then we have to multiply it by the minor. Now the minor, when I delete the first row and the first column, I'm left with this other matrix, right? This smaller 2 by 2. Right? But it also is upper triangular because I still have a 0 there. So it's like we're back in this case, right? So let me write it A33. But look at what happens. So I have my A11 there. -1 squared is 1. And then when I compute this 2 by 2 determinant, I'll have A22 times A33 minus A32 times 0. So this is 0. So when I write it down, look at what I get. I get A11 times A22 times A33. Pretty interesting. So if you notice the pattern here, the pattern is when I have an upper triangular matrix, in this case it was 2 by 2, when I computed the determinant, all I ended up doing was multiplying these elements on the main diagonal. That's right here. In the 3 by 3, even when I did my cofactor expansion and I used like a good choice, meaning I chose this column that had, two zeros in it. I could have chosen the third row because it also had two zeros, but I went for the first column. We did our expansion. The terms that were zero, that really helped us. But then we ended up getting this as the determinant, A11 times A22 times A33. The same elements are here. Now, I don't know about you, but if this happens to be the general pattern, right? If this happens to be the general pattern, then this is certainly an easy calculation. This pattern that we're seeing here would imply that the determinant of a upper triangular matrix is simply the product of the elements on the main diagonal. So unlike the trace, where you add up the elements, for the determinant, you would multiply them. But that seems to be the case for the upper triangular. Let's see if we can somehow generalize this pattern for the general n by n upper triangular matrix. So let's see if we can write that down. Right? So it's going to be A11, A12, A13, and then it will go across to A1n, right? And again, this is where we will have to kind of use our powers of deduction or reasoning to say, okay, yes, this pattern will continue. But what I know for a fact is I'm going to have a bunch of zeros below each of these entries on the main diagonal. So I'll have to have a 0 there and a 0 there. And then your A23, A2n, then your A33, and again all the way down you'll have a 0, all the way down until you get to that n position, and so forth, right? So that's the general n by n upper triangular matrix. And the thing is, if I wanted to find the determinant of this, again, I would choose that first column. So if I did my first column, it will look something similar to this. I can ignore all the entries or the terms that would be multiplied by 0. So I'll have A11, and then I will have times C11, and that's it. All the other terms will be 0. So plus dot dot dot, right? Well, let's write down what C11 would be. So it's going to be A11, and then I would have negative 1 squared, and then it will be the minor of the 1, 1 entry, which means I delete the first column and the first row, and I am left with this. A22, A23, A24, dot, 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 A2n. And again, below, because I started with an upper triangular matrix, I'm going to have zeros again below this diagonal entry. And then this will be A33, A34, dot, 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 A3n. And again, I will have zeros below this one. And then my A44 all the way across the A4n. Zeros all the way down, and then A and N right there. And then I have to find that determinant, right? So this is a positive 1, so I don't need to write it. But then to compute this determinant, I will use the same procedure. So I'll have A11 there, and then I'm going to choose to use, again, the first column, right? So in this case, I will have A22 times negative 1 to the 4th power, right? And then when I block out this column and this row, I'm going to be left with this. submatrix, the 3, 3, and then the A3, 4, dot, 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 A3N, and then the zeros all the way down, and then A4, 4, zeros all the way down to A and N, right? But then each time if I use my first column, delete the first column in the first row, I'm going to be left with another upper triangular matrix. And then this pattern will continue. So again, I would choose A3, 3, right? So I have A1, 1, A2, 2, A3, 3, and then times, and now it's going to be -1 to the 6th power, right? Actually, now that I think about it, I don't even have to do those powers, because each time I start over, this entry is now in the first row, first column. So these should really just be 2's. It doesn't change the result, right? I was just looking at the subscripts, applying the definition. But each time we start with a new submatrix, we're taking that entry in the first row, first column. So all of these are to the 2nd power, right? And then I'll write, this is the last one that we will write down, and then I'll have the A4, 4, and then all the way across to A4N, and then zeros below, and then dot, 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 your ANN. And then, so again, we have an upper triangular determinant using that first column. Again, we pick out the A4, 4, and then that pattern continues all the way down until we get to A sub NN, right? So this is going to be equal to A1, 1 times A2, 2 times A3, 3 times A4, 4 times dot, dot, dot times ANN. So we end up getting the product of the elements on the main diagonal, right? And it turns out this is also true for lower triangular matrices. So any type of triangular matrix, diagonal included, the easy way, and in fact it's the only way you should even think about doing the determinant of those matrices, is simply by multiplying the entries on the main diagonal. So let's write that down as a theorem, right? And this one is telling us how to compute the determinant of triangular matrices, right? And of course, triangular matrices include the diagonal matrix, which is both upper and lower triangular, right? So if A is triangular, then the determinant of A is simply A1, 1, A2, 2, A3, 3, dot, 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 to ANN. Just the product of the elements on the main diagonal. And just like how there's a nice symbol for a sum, there is a nice symbol for a product as well. It's actually uppercase pi. So you might see this formula written like this: the uppercase pi meaning the product, and then we could say k going from 1 to n of the a k k's, right? So this is a really useful formula for finding the determinant of triangular matrices. So here are just a couple examples, right? So no matter how big the triangular matrix is, right, we can use this result to find its determinant. So if A, let's start with the 3 by 3, right? So let's say it is an upper triangular matrix with these entries, say 1/2, right? As soon as you recognize that it is a triangular matrix, if you're asked to find its determinant, so the determinant of this matrix is simply 4 times 8, times 1/2, which will be 16, right? It could be bigger, even if it's like, let's say it's a 4 by 4, and if this happens to be a lower triangular matrix, it works the same, right? So let's say it looks like this. Right, so let's say we have that matrix. Again, we realize that it is a lower triangular matrix. All the entries above the main diagonal, those entries are 0. So its determinant, and I'll use this notation for the determinant just to remind you of the different notations. It's the product 10 times 2 times -1 times 4. That gives me -80, right? So triangular matrices, very, very easy to find the determinant. If you have a diagonal matrix, just as easy. You know, here's a 5 by 5 one. Right? Who would think we'll be able to do a 5 by 5 determinant so easily? Right? Well, if it happens to be triangular, then yeah, we could do it very easily. The determinant of this matrix is 1 times -2 times 3 times -4 times -5. So what do we have there? This is 20, 60, -20, and that's our determinant, right? So I don't think you could ask for an easier formula for determinants. Now, unfortunately, not every matrix is going to be a triangular matrix, right? You know, so what if I had just even one entry above the main diagonal? Then unfortunately, this whole process couldn't work, right? But it turns out that all is not lost, because if the matrix is not triangular, well, we have a procedure for creating triangular forms. In fact, it goes all the way back to Gaussian elimination. That's what we did, you know, to make it easier to solve linear systems, by eliminating certain terms. And we can do the same for determinants. If the matrix is not a triangular matrix, can we use our row operations and make it triangular? Absolutely we can. The thing, though, is that we have to first understand how those row operations will affect the determinant, right? So that's going to be our next little foray. And so we're going to say, so our next one will be using row operations, right? Now, based on our cofactor process, that process, it shows us that no matter how large the determinant is, we can slowly break it down until we get to 2 by 2 determinants, right? It might take a long time, but we can break down, for instance, 4 by 4s into 3 by 3s, and then those 3 by 3s into 2 by 2s, and then we can compute them using our 2 by 2 formula. So in principle, every determinant can be broken down to 2 by 2 determinants. So if we can figure out how row operations affect 2 by 2 determinants, then at least intuitively, you know, we would get a sense of how it affects the larger determinants. So that's what we're going to do here. We're going to start with our generic 2 by 2 matrix, so A, B, C, D. We know how to compute its determinant. So the determinant of A is AD minus BC. So now let's ask ourselves, if we performed, you know, our 3 elementary operations on this matrix, right, and produce a new matrix, how is the determinant of the new matrix going to relate to the determinant of the old matrix? So we want to get a sense of how performing our row operations will affect the determinant. All right, so let's see what that looks like. So let's do a row swap, right? Now, again, with only two rows, we don't really have much of a choice. So what we're going to do is form another matrix. I'm going to call it A1 by simply swapping rows 1 and 2, right? So here is A1 that's produced by performing this operation. That means CD is now the first row, AB is now the second row. Let's compute the determinant of this matrix and then see how it relates to the determinant of the first matrix. So the determinant of A1 is C times D. Right, so, oh wait, this should be a B. Just realized I wrote down two D's. So this is a B. So the determinant of this matrix is C times B minus D times A. Well, I mean, we know that we know that multiplication of real numbers is commutative. So this C times B is the same as B times C. And of course, D times A is the same as A times D. And then look, if I factor out a -1 here, then this becomes negative BC plus AD, which I can write this as the negative of AD minus BC. So it looks like, not that it looks like, but that is the case. When you perform a row swap, it changes the sign of the determinant. Notice that this number is the opposite of this number, or vice versa. This number is the opposite of this number, right? So if we perform a row swap, it changes the sign of the determinant, right? And so we're going to have to keep these properties in mind as if we decide to use row operations to help us compute determinants. All right. Let's see what happens if we multiply a row by a constant, right? So with, let's say our constant is not equal to 0, right? Because we don't multiply rows throughout by 0. If we do k times row 1, right? I'm going to call that matrix A2, right? And that will be k times, and what I'm doing it is to the original. So I'm not looking at this one. I'm saying if I start with this original matrix and I perform each of these operations, how will the determinant be affected? So if I take k times row 1 of my original matrix, I have ka times kb, and then I have cd. Now let's compute the determinant of this new matrix. So the determinant of A2, it's this product, so it's KAD minus this product, KBC. And then now notice we have a factor of K in common, so I can factor out the K and I'm left with AD minus BC. And again, look at this. So when I multiply a single row by a constant, it looks like the determinant gets multiplied by a particular row. All right? Now, the way we're going to utilize this property is going to be a little bit different, but at least we've established the relationship that if I multiply a single row by a certain constant, then the determinant gets multiplied by that same constant. All right? Okay, so we have 2 out of the 3 operations covered. Let's look at the last one. And for that one, I'm going to do k times row 1 added to row 2. So using the same constant there. So if I now take k times row 1 added to row 2 and produce a third matrix, let's see what happens. So this operation does not affect row 1. It's going to be A, B. But what I will have is I will have C plus K times A, and then D plus K times B. Right? That's the effect of taking my original matrix. You can still kind of see it there. But if I multiply the first row by K and add it to the second row, this is what I will get, right? Now let's carefully go through and compute the determinant of this matrix to see how it compares with my original AD minus BC. So the determinant of A3. So it's this product, so it's A times the quantity D plus KB minus B times the quantity C plus KA. Right? Well, let's distribute to remove our parentheses and look to see what we can simplify. So we have AD plus KAB, I'll write it like that, and then minus BC, and then a minus KAB. Now that's pretty interesting because look, this term and this term, they're opposites of each other. So it's going to cancel out, or they're going to cancel out, and we're left with AD minus BC, which is just the determinant of the original matrix. And so this is pretty cool. Here, not only is it cool, but it's interesting, and it's going to be very, very useful. Because this is saying, remember, this is the operation that we use the most as far as eliminating entries. So, this particular result is showing us that when we perform a times row and add to another row, the determinant is not affected at all. Very, very cool stuff. All right, so let's kind of summarize these three properties, just like how we summarize the ones for triangular matrices, right? So this is our theorem, and this is our performing row operations on determinants now, right? So row operations on determinants, like how are the row operations going to affect a determinant? Well, we just saw it doesn't. There's this one in particular doesn't affect it at all, which is exactly news to our ears, right? So, so if B is obtained by swapping a pair of rows in A, right? So if we obtain B by swapping a single pair of rows in A, then the determinant of B is going to be the negative of the determinant of A, right? So that's the first general principle that we have regarding the effect of row operations on the determinant. So if I start with matrix A and I swap a single pair, so I do one row swap, the matrix that I get, its determinant will be the negative of the determinant that I started with. All right? So that's a row swap. What about times a row? So if B is obtained by multiplying a single row of A by some non-zero constant, right? Remember, we never multiply an entire row by 0. So if we're multiplying a row of A by a non-zero constant K to form the matrix B, then this is what we can say. The determinant of B is going to be K times the determinant of the original, right? So again, if I multiply a row by a constant, any row in A by a constant that's not equal to 0, and I produce a new matrix B, then the determinant of the new matrix is going to be K times the determinant of the original, right? And then our last one, now this operation is the most complicated one to describe, but it has the least effect on the determinant. So if B is obtained by adding a constant multiple of one row of A to another row of A, right? Then the determinant of the matrix that I get is going to be exactly the same as the determinant of the original matrix. And this is key for us because this is the operation that we can use to start with a non-triangular matrix slash determinant and turn it into a triangular one. And this is saying, if for instance, if all the operations I use involve just adding a constant multiple of one row to another, then the determinants are going to be the same. Let me just kind of illustrate this one fact, right? So we're not going to do a full example now. I want to save that for the next video. But just to illustrate what this is saying, right? So we're not going to evaluate the full determinant, but just demonstrating each of these three, right? So these are examples, but not full examples, right? I want to save the full examples for their own video, right? So let's say we have 3, 1, 2, negative 9, 8, 1, 0, 0, 4, 4, 7, 10, negative 1, 6, 11, right? So this is a pretty big determinant. And even though we have a couple zeros, right, it would be still a bit of work to evaluate this using the cofactor expansion, right? So what I'm going to do is do just, so for instance, if we were to just swap a row, or swap a pair of rows in this matrix. So let's say I wanted to get the negative 1 up here where I like to have my positive 1, right? So if I were to swap row 1 and row 4, I would have, this is what the determinant would look like. And notice I'm using the vertical bars, not the brackets now, right? So when I do this swap, right, so row 4 goes up top, row 2 stays the same, row 3 stays the same, and then row 1 goes at the bottom. Well, I know that these are not going to be equal. These are going to be the opposites of each other. So this determinant is going to be the negative of this determinant, right? And that's because I did a single row swap, right? Now, suppose I wanted to eliminate this 8, right? Let's say I wanted to eliminate this 8. And in fact, that's what I would want to do. In fact, I would want to eliminate everything below the main diagonal because then it will become a triangular matrix, right? But again, we're not going to do it fully. I just want to show you, since we mentioned these properties, what they kind of look like. So if I were to take 8 times row 1 and add it to row 2, So if I did this, 8 times row 1 added to row 2, I would still have to bring down my negative sign, and I'll give myself a little bit more room. And then what would happen is there would be no change in the determinant. I can eliminate this term and not worry about changing the determinant. That's what that theorem that we just proved. At least we proved it for the 2 by 2, and then by extension, intuitively, it should work for the other ones, and it does, right? So if I take 8 times row 1 added to row 2, I will have 0, -7, 48, and 88, and then everything else will stay the same, right? And what we have now is with these equal signs, all 3 of these determinants, right? Like with the negative in front here and here, these 3 determinants have the same exact value. And what we would continue doing is eliminating the entries below the main diagonal. And then once it's triangular, then we will use the previous property, right? So that's essentially, that's going to be our approach, right? If we need to evaluate really large determinants, we're not going to use the cofactor expansion. It takes way too long, way too tedious. What we can do is we can use a series of row operations, make the determinant triangular, and then take the product of the elements on the main diagonal, right? So if you want to see a full example of this, why wait? Just tune into the next video. See you then.